So and that's what I was saying here, is the like factors, or the common factors, give us higher multiplicities. Because that x minus 1 showed up twice, I would have a multiplicity of 2. And some of us did write this out where we said 0 is equal to x minus 1 again, and you can do that. Notice, how many times do you give 1 equals x?
Yeah, I read that.
Twice. So that's why it's a multiplicity of 2. Does that clarify that detail? Okay. So what are the zeros for f? X is equal to?
X is equal to 0, x is equal to
X minus.
yeah.
And x is equal to?
X.
Like, what's the 0? Not give me the factor. What is the 0? X equals 1. Those are the two different zeros. What is this multiplicity?
2.
Multiplicity of 2 and a multiplicity of what? 1. Do you notice I am shortening multiplicity? Traditionally write it all the way out, but. So I want you to notice this. 3, what do you notice about the zeros of a function counted with the multiplicity and the degree of the function? How many, what was our multiplicity here? Total, 3. What was the degree? 3. What was the multiplicity, or the total of the multiplicities here? 3. And what was the degree? 3. What was the multiplicity here? 2. Well, it was 1 each, which would give us a total of 2, and the degree was 2. So what do we want to notice about the zeros of a function? So we would need to, but what are you doing to all the multiplicities to get the same as the degree? You have to add them. So we want to say the sum of the multiplicities for each zero is the same as the degree. The sum of the multiplicities for each zero is the same as the degree. That is an important detail. And I do want to point this out. Did we say the sum of the multiplicities for each x-intercept? No, because what kind of zeros can we get that would not be x-intercepts? Complex, the imaginary ones, right? So that's an important distinction, that it's the sum of the zeros and their multiplicities, not necessarily the sum of the x-intercepts, because you can totally have complex zeros. Alright, so is it a fair saying that we need to practice multiplying some polynomials and some factors? Yes. We're not going to take long here because we have got to get to the next portion. But I do want to point out this detail here, right? This is a way, this is 4.3, so I think we skipped 4.2 in the textbook.
176.
176, thank you. Can I erase this part about the sum of the multiplicities? Okay. So here is a model of a way to multiply binomials. Please notice, why do I call this a binomial? Because it's got 2 terms, right? So this is a way, it's called an area model of how we would multiply binomials. All it is doing is helping you distribute, okay? So when we have x plus 2 times 3x minus 2 times x plus 4, notice how they only multiplied x plus 2 times 3x minus 2 first. In the same way, if I do 2 times 7 times 5, I'm only going to multiply 2 of the numbers first. And then that product is multiplied by the last factor, right? So I'm going to multiply 2 of these first. We go with that idea. Okay? You can use whatever method you want. I personally don't ever use this area model. Here's how it's set up though. So you set up a little box for each factor. Because it's a binomial, how many things do I need? 2. So they did the x and then plus the 2. And then here would be 3x and then a negative 2.
It's like the genetic things we did, where you did like
Punnett squares?
eye, brown eye, yeah.
So it's similar in ways, but this is just to help you distribute. What is 3x times x?
3x squared.
What is 3x times 2? What is x times negative 2? And then negative 2 times 2? Negative 4. And then look for your like terms. Do we have any like terms? 6x and negative 2x. So you would add those together, and 3x squared plus 4x minus 4, that is the product of those two binomials. Now I still need to multiply it by x plus 4. But it's exactly the same process if you do it from here, except you would need how many along here? 3. We have 3 terms, so I need 3. 3x squared, a positive 4x, and a minus 4. How many columns do I need? It's only 2 terms. So x and 4, and a positive 4, so yeah, so plus 4. And again, distribute. What's 3x squared times x? 3x to the third. 3x squared times 4? 4x times x? 4x times 4? Be careful. And just use calculators for that stuff. And then negative 4 times x? And negative 4 times 4. Does anyone see any pattern that might be helpful to identify like terms in this method?
The ones across.
What would we call those? There's a D word I would use to describe them. I would call them diagonals, right? The diagonals are giving me my like terms. So if you like this method, go for it. So the product of all 3 of these binomials is 3x cubed plus, that's a positive and a positive, so it's 16x squared. 16x, that's negative, so minus 4x gives me 12x, and then just minus 16 at the end.
Look, just making it longer.
Well, we're getting the standard form, right? And this is just, I'll be honest with you, I would never go from factored form to standard form, but teachers in the future are going to expect you to do this. It's a skill that we need to develop, okay?
To add that to the first one.
No, we're not adding it. Notice what we did is we multiplied all this out to get this. This is standard, this is factored, but they should be the same, meaning they are what? Equivalent. Those are 2 different forms of the same function. Just like we had vertex form and factored form and standard form, we can get each form for every quadratic function. They look different, but they're the same story.
In the first two, like when you have to just put it together. Like.
Well, so remember, this right here is from the first table. That is this part, and so I have to take this and then multiply it by the x plus 4. Because I haven't multiplied by x plus 4 yet.
We gotta do
Does
that.
that make sense?
We gotta do all of that for everything.
We're not going to do all of them because we don't have that kind of time. But a quick note I want to make is this. You do not have to use that table. There's a D word that I kept using to describe what we're doing in this table. What are we really doing? We're just distributing. The table is a way to help organize the distribution. Personally, I'm never going to do it that way. I'm going to start with my first 2 right here, and I'm going to distribute. X times 3x is 3x squared. X times negative 2 is minus 2x. 2 times 3x is plus 6x. 2 times negative 2 is minus 4. Times, all that's being multiplied by x plus 4. I would then simplify. To me, that's a little bit less work, which is why I prefer that method. Do you have to use the distribution like this that I do? No. If you're more comfortable with the table, use the table. It's called an area model. If you like this method because you feel comfortable with it, do it. Now, I will point out the one tricky part about distribution here is this 3x squared needs to be multiplied by x plus 4. What does this 4x need to be multiplied by?
Same thing.
Same thing, right? So you have to show that distribution, but 3x cubed plus 12x squared, then 4x times x is plus 4x squared. 4x times 4 is plus 16x. Negative 4 times x is minus 4x. And negative 4 times 4 is minus 16. And you do have to pay attention to where your like terms are. Same answer or different answers? Same exact answers, right? So does it matter which one you use? So which one do you need to use? The one you feel more comfortable with. I don't care. You just need to get the right answer. All right? So I'm going to leave this up here so you can refer to it later, but I do want to point out 1A, you need to answer this. How can you use graphing technology to verify that the expression in factored form is equivalent to the product written in general or standard form?
Maybe set them equal to each other, will it?
Maybe. It will on a cast version, but not this. Say again. Graph it. If they are equivalent, the graphs will be the same. There we go. That's what we want to recognize. That's the most effective way to do this. So let's go here. So I started out with, what was it? X
Plus.
3x minus 2? Was that what I did first? Times x plus, no, x plus 2 times 3x minus 2. Sorry, you were telling me the right thing, KJ, and I shut you down. X plus 2 times 3x minus 2, and then what else?
X plus 1.
Okay? So I might want to zoom out just a hair, just to see that a little bit better. Alright, so there we can see it for the most part. Now I'm going to type in that standard form, which was
3x cubed plus 16x squared plus 12x minus 16.
yeah, make sure you pay attention to those squares plus 12x minus 16.
Yeah.
So are they the same?
Yeah.
Yeah, literally we can't even see the other one because they're right on top of each other. So are they equivalent?
Yeah.
Yes. So can you use this to help check and make sure that you have the right product every time?
Yeah.
Yes. Take advantage of that.
So how many do we do?
That's a good question.
All of them.
Ooh, before we get to that, we actually need to talk about part B. This is critical. And this is on your graphic organizer because you've got to know about part B. Make sure you write 1A, and then we're going to talk about 1B, and then I'll talk about the next part. I'm probably going to have each group do 2. The Fundamental Theorem of Algebra.
What is that?
That's kind of important, isn't it?
graph.
Let me check something real
They
quick.
are equivalent, you can graph it.
Because I think it's in the textbook, and I do want you to note it if it is. There we go. So if you go to M1-110, go to M1-110 in your textbook really quickly. Hold on to the page that you're currently on because you're going to come back to it in a second. Okay? This is an important principle. The Fundamental Theorem of Algebra states that any polynomial equation of degree n must have exactly n complex roots or solutions. Any root may be a multiple root. What would we call that multiple root now? Multiplicity, right? When we have 3 of those same roots, it's a multiplicity of 3. So you need to note this fundamental theorem of algebra, and just for now, don't write out the full definition, just write out what page it's on, because the more time you come back and you reflect on these things, the better off you're going to be. So M1-110. The pink, oh yeah, and on that other page too. So when we come back to here, just put the page number on the graphic organizer and on that page, yeah, go ahead and put it on that page right now that you're on. But the page number is M1-110. So how does this cubic function demonstrate the fundamental theorem of algebra? Well, what's the degree of a cubic function? 3. How many zeros did we have? 3. That's important to notice, right, that the degree was 3 and there were 3 roots. Right? So obviously this part shouldn't go under 1b. I'm running out of space. But for, or 1b. 1b, the number of zeros of, and I'm going to even say complex zeros, because is a real number complex?
Yes.
Yes, right? A real number is complex, so a real number is still a complex zero. It's just not an imaginary zero. So the complex zeros, number of complex zeros, matches the degree. Right, the degree being 3. The fundamental theorem of algebra tells us that whatever the degree is, that's how many complex roots there are. That is huge and important to notice. But note that on this page about M1-110 talks about the fundamental theorem of algebra. Okay. So let's do this. Group 1, I want you to do A and ooh, this is a good
Just
problem
A.
to have. Nope, not just A.
Yeah,
Well, there's
yeah,
four
yeah,
problems.
yeah,
You
yeah,
can always
four
do
groups,
one.
yeah, four.
It's true.
What?
But I need you to do 2 each. Let's go A and B. Group 2 do A and B as well. Groups 3 and 4 you're doing C and D. So group 1 you're doing A and B. Group 2 you're doing C and D. Now I want to point this out really quickly. Do not follow all the directions. I just want you to follow these first 2 sets of directions. Determine each product algebraically, show all your work, and then use technology to verify your product is correct. Don't sketch the graph on here.
Just do that.
Just do that part for now.
So I was just distributing that bit.
Yep. It is the product of binomials just distributed. Groups 1 and 2 do A and B. Make sure you're talking with your group, helping each other get better at this.
So what? After we keep-
Don't forget, once you're done with the product, check to make sure you have it right.
Yeah, we graph that and then we put it in factors or
So graph, you would need to graph both forms, right, to make sure it is, they are equivalent.
This one and this one, now, for the third one.
Say again? Right, because if you only graph one of them, there's no way to check to make sure they're the same.
So I have to graph like this and
And then the product, or the standard form.
For the first part, I don't get 3x plus 2x minus 6x plus 4, but for this last one,
So first off, I would simplify that, right? And then I would put brackets around this, and I would keep that 2x plus 1 so that you remember to distribute to the 2x plus 1 as well.
So would it be X
Okay.
plus 2?
No, you gotta like write it all out.
Oh, shit. So X plus 2 3 times.
Did you get 0? Was -1 times -1? Be careful.
I haven't got to finish it yet because.
So don't forget, how can you check to make sure that you have an equivalent standard form to the factor
Negative 3x
form?
plus 2x minus
Graph
6x
it.
plus 4.
Huh?
Yeah, and then combine like terms, negative 3x squared minus 4.
Well, you need to check to make sure you did it correctly.
Yeah,
Times
yeah, but we thought that.
2x.
Hopefully, yeah, hopefully you're done because you got it all correct.
Yeah,
Yeah,
now
yeah.
I gotta distribute.
So negative 3x squared.
Good, make sure your whole group recognizes this. Because if you don't write it out this way, you'll get the wrong answer.
Oh, like.
All of your group gets that, yeah, yeah.
worked it out already.
Cubed. And then negative 8 squared plus
Oh, that's a pretty square.
8x, and then the other one just becomes 1, so.
Well, we're not doing the last two.
Just do that first one first. So were they equivalent? Made a mistake? Let me see. And then you put minus 2x, but it should have been plus 2x. And so, that's one of the reasons why we want to graph it, to make sure that we're doing it correctly, because then we can correct our mistakes when we're doing homework or tests or things like that.
What did you get for your last one?
Alright, so.
I didn't get nothing like that.
I'm not gonna-
Okay, well, it's only when you're done. 'Cause
Is
I
it?
finished and,
Well, something wrong.
so I'm gonna just go ahead and grab it, and so then maybe I'll.
I think it's negative 3x plus 2, right, so it'll change things. So, don't forget, like, you don't have to just follow up there, make sure you're thinking through it, right? This is just, you're multiplying, so negative 3x times x is negative 3x squared. What's negative 3x times 2?
Negative 6x cubed
You gotta be
minus
careful about the signs,
11x squared
right?
plus 4
2x
x
positive
plus
4.
4.
And it looks like you're doing that correctly, but
Okay, I got
you're
it.
overthinking it instead of multiplying. That's all you're doing is multiplying, right? Now, don't
The
forget,
only difference
so what is
is
2x
I got
minus 6x?
negative 11x squared instead of 5x
Is
squared.
it 2x?
Would you get the 5x squared?
Negative 4x, right? Because one's negative, one's positive. Positive 4. But remember, and that's what I'm saying, just do the first two first. Now you need to multiply it by the 2x plus 4. Okay.
Well, see, I always think, well, I always think
Negative
you add
three
in terms like negative 8x
Now,
squared.
no, you can't do the variable in there. You can do negative 3 times 2 though.
How do you know whether to add or subtract? Did you just take the negative from the
Just
30
subtract.
and then like use that as
So
a
because
function then?
that would
Because I.
be negative 6, and what's x squared
He
times
should have
x?
given us the same thing though, because
X
y'all did,
cubed.
adding and, or subtracting the negative and I did adding the positive or whatever. You know, the full swabby swap thing. Like I did negative 8 plus negative 3, which would
Wait,
be
how do I multiply?
whatever.
Wait, do I just?
Isn't
Oh,
that
yeah.
what you did up here to multiply?
So you
Now, I'd probably do it over
already
here so you
did
have enough
so
space.
You
I'd
said
do
5x
negative 3.
squared.
Well, you can and distribute it like that, but remember what I'm saying is you can just use that if you feel comfortable with that, right? But you're gonna have negative 3x squared, you're gonna have a minus 4x, and you're gonna have a plus 4. And then up here, you're gonna have that 2x plus the 1, so you need 3 rows this time. Yep. And then the same exact thing, right?
Okay, so this is the graph I got for this one. Now, somebody when,
You need to graph that one as well, to see if they match on top of each other.
this one should do.
You're about to ask someone else to do it.
Yeah, I didn't
Type
think
it
you
in
could
there.
do a second one. It never lets me go back up to the X thing.
It does. So first off, if you're already graphing, you just hit tab and it opens it.
Oh,
But also remember menu, graph entry / edit, enter a function. That gets you to there as well.
I did something.
So do y'all want to try mine? Like you did, what do you do?
I'm really glad that y'all noticed to do the x plus 2 times x plus 2
Okay,
times
well,
x
let's
plus
try
2.
mine, I guess.
If you don't do that, it'll 100% give you the wrong answer. So good job on doing that. Did you check all of them, make sure you have the right answers? Okay.
Hey, can you show me what you got for the one equivalent to ours?
2x times negative
Which-
4x is.
Hey, I think I got it right. That's what mine does.
Are they like exactly?
I don't know, I'm trying to say, I'm gonna try again. Ah, maybe it's just eight.
Or negative 4 times 2.
Yeah. Let's go for 8.
Because instead of doing negative whatever minus negative, I did negative whatever plus negative, well, it's like, I think you did minus, and you used that as the like negative, but then it made it into a totally different. Oh, raised to?
Oh, you're right.
I think, I need to check that.
Why did this wrong?
Nope, I missed something,
Yeah.
hold on.
I got
Oh,
it.
shoot.
It's the same.
No, I did it right. Yeah.
Yeah,
Can't
okay.
do that, you can't do it, but
That black line is two equations.
Doesn't matter.
I would just,
I mean,
I could do it.
So,
check it.
I know exactly what it was on the part that you said,
-3
what was the number
plus
you got
-8.
5, and you said it was.
That's -11, -8 plus -3.
Okay, so instead, it should be -8x squared plus -3x.
That's one way to do it.
That's.
Well, -3x squared, right?
Yeah, but that's the only difference they had is they did, they used the negative of the 3 as a minus, but I added them.
Well, adding a negative is
I
subtracting.
know, that's what I said, that's why I asked, that's why I told my dog it's weird that we got two different things.
But if you have, yeah, but notice if you have -8x squared, and then you do -3x squared, right? Or you write it this way, type it in your calculator, it's -8 minus 3.
Go with no one.
Yeah, so-
Go to the calculator. There you go.
That's what I was saying, I didn't know how we got different things, because it would be the inverse.
Y'all are just trying to do it in your head, and made an error there.
I don't know, I didn't do nothing in my head, I
So I
had to,
did everything right, just that two
yeah, you'll be fine.
I did the box first.
Remember,
Yeah, you're not
the exponents
like-
only change when you do what? When you multiply.
For the second one, have y'all?
The exponents only change when you multiply, but you add and the coefficient changes. If that makes sense.
I said two, I mean, I'm just not.
Well, I mean, how can you check to see who's right? Graph them, okay, but we're gonna talk about it real quick. Alright, can I grab everyone's attention, please? So I have the answers for A, B, and C up on the board. We're gonna talk through D a little bit more heavily. I may have made an error doing it mentally, but is this what we all got on A, B, and C? Yes? No differences or discrepancies?
That's what
Okay.
I'm done.
Yeah, I got
Honestly, practice, but like it's just learning to distribute. I know that 2x times x is 2x squared. I know that 2x times -1, that's just -2, and then that's gonna be a like term -1, so -3x. And I do a similar thing over here, is I know -3x squared times 2x, that's the only one that's gonna give me x cubed, and it's -6x cubed. I know that the way I'm gonna get x squared is from this term multiplied by this term, and so it's -3x squared. But I'm also gonna get x squared from these two, right? So I just block off the terms that go together. But it's just practice. I don't recommend that for you. Yeah, don't do that in your head. Okay, let's talk about D. Actually, there's one thing I want to talk about before I even do that. So, if you tried to do -3x squared minus 8x squared, that's how we got this minus 11x squared. Can you type the x squareds into the calculator, Nathan? No. What's it tell you? Variable is not defined. You cannot do things with the variables, like adding and subtracting, on this version of the TI Inspired. If you have what's the CAS version, it can do that. However, all you have to do is -3 minus 8. Those are like terms, so you have -3x squareds, then you have another -8x squared, so it's -11x squared. Just do the coefficients, okay? And I do want to point this out because this was coming up with root 3. Do I do anything with the exponents here? No. The exponent only increases when you're doing what? Multiplying. Because literally what is an exponent? Repeated multiplication, right? So it's only when I multiply that the exponent increases. We good with that idea? Okay. Yes, alright. All groups who did D, I want to commend you because most students make this mistake. What is the first thing I need to do when I have x plus 2 cubed? Most students want to just write, hey, that's x cubed plus 8. Because what do they do? I know y'all are better than most students. What are they doing to get x cubed plus 8? Well, the cube, right? They're distributing and just looking at that cube. So I do want to point this out. So we're going to come back to the multiplication in a second. But if I do x plus 2, nope, that's not what I want. I want x plus 2 cubed. X plus 2 cubed, is that the same thing as x cubed plus 8? No. So that is why we have to do the x plus 2 times the x plus 2 times the x plus 2. We good with that idea? Okay? So you can use the chart if you want, the area model. Totally okay. Most of us weren't using the area model, so I'm not going to use that right now. But remember, we're just going to distribute x squared plus 2x plus 2x plus 4. And then I'm going to simplify that before I multiply by x plus 2. So x squared plus 4x plus 4 times x plus 2. Once again, I'm distributing. So x cubed plus 2x squared plus 4x squared plus 8x plus 4x plus 8. Is that what we all got up to this point? Yes?
Yes.
And then I get x cubed plus 6x squared plus 12x plus 8. Yep. Was that equivalent to the factored form? Mm-hmm. The only thing at this point that I would note to myself, if I'm going to use this practice here to help prepare for the test, is I would make a note to myself here, graph both the factored and standard form to check equivalency. Graph both the factored form and standard form to check equivalency. That is the last note I would make here to myself, to use this to help practice. I said, oh, that's obnoxious, it was already there. Yeah. Graph both factored form and standard form to check equivalency.
What was the particular option? Understanding
Okay, so graph both the standard form and the factored form to check equivalency. Okay. So, we already addressed this a little bit. Max determined the product of 3 linear factors. X plus 2 cubed is equivalent to x cubed plus 8. Is he correct?
No.
No, why not? He distributed, and this is an important thing, he distributed the what? The cube to x and 2. And he should have distributed, but what should he have been distributing? So there's an F word to describe that. Factors. Right? He distributed the cube to the x and 2, but he should have distributed the factors. That is what x plus 2 cubed is. Okay? And don't forget, we checked it.